Hi, everyone. Welcome back. Hopefully you had a nice break and got outside and looked at the earth in its native form, not inside of a room with a screen in front of your face. This next session, I get the honor of carrying us through to the end. Hopefully everyone is pumped up, because I am. This is where we get kind of like a little bit nerded out in some of the machine learning and other cool topics. So hopefully everyone's fired up. If not, you will be, and then we'll be done and get you out of here by 4 o'clock for sure today. So thank you for those of you who have stuck it out with us and continue to enjoy these dialogues. Just a couple of reflections before we get really started. I want to just acknowledge there's partners. This whole effort, we've done this for 6 years and iterated in this area for a reason, and it's because we feel like we're building capacity in all of California. This is not about the Office of Information Management Analysis. This is not about the water boards even. This is not even about the water community that already works together. This is about increasing and building the capacity of all of us. And so you're going to see, and we have seen speakers here that are, some of them didn't used to work for the water board, but now they're part of our team. Some of them have continued to move on and iterate in the space and come back every year and improve on the projects and the data. So this next session is really sort of dedicated to that idea. And really, tying it back to this morning and yesterday's film screening and tomorrow's session, tying that all together, this is about doing things. We're not here just to talk about water data and fully geek out, although we like doing that. We're really about trying to make some changes. And so the whole thread of this year's session is super inspiring to me. So those of you who really want to get your hands dirty, so to speak, on some of this water data to make a difference in society, be sure and tune in tomorrow, because we have an online open planning session essentially to achieve water equity and racial equity outcomes using some of the people, all of you, anyone here can participate and help us make a difference. So with that, I'm going to lead into this next session. The title of the session is From Prediction to Protection. So instead of just navel gazing at dashboards and saying, oh, that's really interesting, I wonder what machine learning could do, we're going to hear some really inspiring stories about people that have taken that and turned it into water quality protection or water resource outcomes that are of value to people. So the specific area that we're going to delve into is using machine learning. And you'll learn a lot in this session if you don't know anything yet about machine learning, but if you do, you'll be even more inspired. We do have some resources, and I'll ask maybe Anna and others to help me, but we have some resources from prior events that we've done that walk people through. For example, Walter Yu from Caltrans has been an awesome partner in Trash Datathon, and he has a whole online essentially teaching exercise on how to do computer vision and what it is and what the latest greatest is. So we have resources for people that want to go deeper. So thank you for that, indulging in me to say all those things. I'd like to introduce our first speaker. Next, there we go. So this is Liam Healey, and Liam is from Lake County Water Resources Department. Liam's going to be talking about this topic, and the title of this talk is Identifying Meaningful Water Quality Parameters for Resource-Constrained Local Governments Data Collection Using Large Open Access State Data Sets. Those are things that we are familiar with. So Liam, go ahead and take it away.
My name is Liam Healey. I'm an AmeriCorps Fellow with the Lake County Water Resources Department, and I will be talking about identifying meaningful water quality parameters for resource-constrained local government data collection using large open access state data sets. And this is a Clear Lake case study in Lake County, California. So hopping into Clear Lake itself, Clear Lake is the largest natural freshwater lake located entirely in California. Despite being very large, Clear Lake is very shallow with a mean depth of only 27 feet. It is also a very old lake, approximately 500,000 years old. Clear Lake is hypereutrophic, which results in frequent and severe cyanobacteria blooms occurring throughout the lake. Even though there are frequent blooms, Clear Lake still provides drinking water to approximately 40,000 Lake County residents, including multiple disadvantaged and tribal communities. In general, there are increasing pressures on the water treatment systems around Clear Lake due to the degrading source water quality. Treatment for drinking water is becoming increasingly complex with extremely high costs of treatment. This is reflected in how residential water bills in Lake County are more than double the California state average. Clear Lake is also considered the bass capital of the West and is a huge source to the local economy. So Clear Lake itself has 3 distinct basins where water quality was sampled at historically by the Department of Water Resources. These 3 basins are shown in the map on the left-hand side, with CL1 being the upper arm, CL4 the Oaks arm, and CL3 the lower arm. So historic water quality sampling by the Department of Water Resources was done 10 times a year, with metals done 3 times a year. And in total, there were 49 lab analysis parameters collected, not including any of the field data. These lab analyses were done at Bright Chemical Laboratory, and this was a very expensive and labor-intensive sampling effort. So in terms of a little bit of timeline of DWR's historic water quality sampling for Clear Lake, they began sampling water quality data at the CL1 and CL3 sites in 1964, then added the CL4 site in 1968, and then jumping ahead to 1991, they briefly stopped Clear Lake water quality data collection, but then resumed again in 1998. In 2006, TMDL went into effect, and then in 2020, DWR unexpectedly discontinued Clear Lake water quality data collection. This brings us to 2020 to present, where the Lake County Water Resources Department began an abbreviated suite of DWR's water quality data collection. So the Lake County Water Resources Department is a resource-constrained local government entity that does not quite have the same capabilities of a large state-funded program, such as the one run by the Department of Water Resources. Right here, I'd like to highlight our parameter list. These are our 49 total analytes that were collected by DWR. So circling back to the Lake County Water Resources Department, and our project goal for this study was we aim to identify the most useful and meaningful water quality data parameters to continue collecting in Clear Lake to both maximize the limited resources and effectively best manage this valuable aquatic resource. So here on the right-hand side are some of our presentation themes that I'd like to highlight in connection with the Data Science Symposium and Water Board objectives. So equity, machine learning, and data accessibility. So with equity, the County of Lake is the poorest in the state of California. And kind of as I mentioned previously, Clear Lake water quality is undoubtedly linked to the economic well-being of the county. As well as with machine learning, through pre-processing this data set, it opened the door for a multitude of deeper analysis, and with the goal of maximizing this utility of this unique long-term data set. In terms of data accessibility, while this data was easily accessible on the CA Water Data Library, it was not quite in a usable format for managers. This project removes that last barrier towards full accessibility and really moving from a full to usable data set. So right here is the open access CA Water Data Library, where we got our water quality data from. The map there shows all of the CL sites where data can be used from. So this is water quality data that I'm downloading here from the CL3 site, and you can choose to easily include field data or not, and export the data into common file formats such as Excel or CSV. So this study analysis was done in our studio with some of the key and unique packages shown here that I just wanted to highlight that were useful for this analysis, as well as the version of R that it was done in as well. So I really like using RStudio for this analysis because pretty much everything can be done with it and don't run the risk of hurting any of the source raw data. So hopping into the analysis itself. So raw data that was downloaded from the CA Water Data Library was extremely messy. This led to a very time-consuming QA/QC process, which I would expect to kind of be the norm for any water data analysis using data from the CA Water Data Library. So some of the key steps that I wanted to highlight that were useful in this in preparing this data for analysis was one, removing duplicates. This can easily be done through the duplicated base R function, as well as moving the data set from being row to column delineated. So originally, this is also shown on the figure on the right, but originally the data set was row delineated. So each analyte was a specific row, and we wanted each analyte as a column and to be represented in date, which made the most sense for organizing this data set for the analysis we were interested in, as well as there were many cases of inconsistent reporting. And this took a variety of different forms with many one typical instances of changing units over the study period. And there was really no common manner of going about this. It just really had to be taken on a case-by-case basis and was, again, a pretty time-consuming working through all the specific analytes and making sure everything was consistent across the study period. So another large problem with this data set was data missingness, as these three figures on the right show as they are missingness figures from the complete study period of 1968 to 2020 for the three CL sites. The x-axis shows a total list of parameters, and the y-axis is the total number of observations, and is also a temporal timescale, with the first observation being representative of 1968 and the final observation representative of 2020. Black and inside the figures represents missing data points, and gray represents present data points. So as you can see, data collection was not quite as continuous as advertised by DWR. So really had to take a more targeted research approach question towards analyzing this data set. So we looked for an area inside the data set where, sorry, the light just went out of my room. So we had to take a more targeted research area and look for an area where data collection was a bit more continuous and whatnot. So this pretty much inside the red boxes highlights from 2004 to about 2020, where data collection was a bit more continuous and with a higher frequency of sampling effort and intensity. So moving forward with dealing with these missing values, the figure on the right shows, again, is the same as the one previously, where black indicates missing values and gray is present. So inside the 2004 to 2020 period, there was a lot more present data, and this really opened the door for more data science analysis. And one approach to handling this missing data was through imputation, and kind of one soft rule of thumb for imputation is there's a 40% threshold to not impute any variable or data set over. And you can see this kind of puts us below that threshold for imputing the data set. Obviously, there's a lot of risks with imputation. You should really check really your constraints and whatnot, and pre and post with the data to really make sure to not give it a blanket case treatment and really be tactical with your usage of imputations. So kind of hopping into the imputation itself, which I'm sure many people are familiar with, but we did impute the CL 2004 to 2020 data. This was done in the mice package in R, which contains numerous multiple imputation methods. And one of our prime examples for guidance on assumption checking was from this source, as well as this figure on the right, which shows two common imputation methods. On the left-hand side being linear normal model imputation, and on the right-hand side being the predictive mean matching imputation. So inside the graph, blue circles represent real data points and red represents imputed data points. Red is lost my slide. All right, moving forward, but I can kind of circle back. Do not have control on my slides anymore. Can you go back a slide?
There you go. I was going to say, if you want to give verbal command, just go ahead.
Okay. Thank you. Yeah. I'll give verbal command. So with the predictive mean matching, it draws real values from the sample data, takes heteroscedastic data into account more appropriately, and aims to reduce imputation bias. If you could go forward another slide. Okay, thank you. So this allowed us to get into the data preprocessing, which in machine learning, just a little highlight with data preprocessing it is a step that in which data gets transformed or encoded to bring it to a state that now the machine can easily parse it. So some of our quick data preprocessing steps were, first off, transform and normalizing data through preprocessing in caret, transforming original data through predict, identifying variables of near zero variance, and then removing near zero variance variables, running correlations, and identifying predictors with high correlations. Next slide, please. So this graph on the left here shows a correlation matrix. So getting into the correlation aspect, where each side of the graph shows our total list of analytes, with darker circles representing high correlation coefficients, and with dark blue being positive correlation coefficients and dark red being negative correlation coefficients. Lighter colors represent lower correlation coefficients, and the default for the core plot in R through the quorum package is to alphabetically order them, which makes it easier to discover trends in or to clusters in the package, but makes it a little bit more difficult to find the clusters. So one manner of dealing with this is through hierarchical clustering, which is shown here on the right, which makes it a little bit easier, in my opinion, with this data set to identify clusters of correlated parameters. So in terms of analyzing the correlation cutoffs, we chose multiple cutoffs at 0.8, 0.7, and 0.6 through the find correlation function in the caret package. You can easily swap out correlation cutoffs, and it provides column numbers that are highly correlated. So in terms of what does this mean for the data, the table on the right-hand side shows our total list of parameters, and with a correlation cutoff of 0.8, you can see here inside the red boxes, these were parameters that were highly correlated after pre-processing them. And then with a lower correlation cutoff at 0.7, you can see again in the red, these are the ones that were highly correlated at 0.8. And then in green, a couple new ones where could be as expected were added through a lower correlation cutoff. And this was the same case for an even lower one at 0.6. So how can this data be used? So circling back to the project goal is to identify the most useful and meaningful water quality data parameters to continue collecting in Clear Lake. With this, it can use this information to determine which parameters are telling us the same things and thus eliminate redundancies and pretty much provide lake managers the information they need on which parameters are the most useful and if they want to kick them or not. As mentioned previously, the Lake County Water Resources Department is a resource-constrained local government entity, and this greatly helps towards saving, can help towards saving the Lake County Water Resources Department money and as well as simplify their sampling effort. And in terms of thinking forward towards future analysis, can determine which parameters should be removed. Another thing I would like to highlight with field data collection, being able to be out and have firsthand experiences collecting field data was extremely helpful for me in understanding the field processes and methods, as well as knowledge of the physical sample site locations and system. And I really think these field experiences helped contextualize a lot of messy data problems that I may have had, and it made it a lot more difficult. Without having these data collection experiences, it would have made it a lot more difficult to analyze the data set. So right here for the slide deck is semi-sample pre-processing ARCO. This will also be available on GitHub as well. Some acknowledgements. I would really like to thank the whole water resources team, in particular, Angela de Palma-Dow and Ryan Carey, as well as Patrick Jarrett, Emmy Fergus, and Ian McCullough for their technical expertise and assistance, as well as all the dedicated staff who diligently collected water quality data throughout the years on Clear Lake. So my references are here, and thank you all very much for attending my presentation. If anyone has any questions or comments, I'll be here, and then my email is also below.
That's fantastic. Thank you, Liam. You packed in a lot and you dealt with some technical difficulties, so well done. Do we have any questions, Peter, or anyone who's monitoring that?
We do not have any questions at this time.
All right, well, I mean, I'd be curious to know, are you like part of the Civic Spark Fellowship? What's the AmeriCorps connection, or is this part of the Watershed Steward?
Yes, I am a Civic Spark Fellow with the Lake County Water Resources Department. Yep.
And do you know that the Water Boards has an employment page? If you scroll to the bottom and you click on employment, you'll find all sorts of opportunities listed there. Just kidding. No, very well done. It looks like we have a question.
Someone's asking if you could share the GitHub link for the project, please.
Yes, I will post that in the chat below.
Thank you.
Are there any other questions? Okay, well, great. Thank you very much, Liam. Love to follow up on some of this work. It's probably reproducible at other kinds of water bodies, but for sure your feedback on the water data structure in the water data library, as well as the approach you took for missing data was very useful. So we'll be sure and pass that on to our colleagues doing open water data work. So thanks.
Thank you very much. I appreciate it.
Yeah, take care. All right, next we have Ryan Searcy, and Ryan has been a partner for many, many years. He's going to talk about a really cool project that has also iterated over time and space. And I'm excited to hear this latest version of it, but he's now at Stanford University at, getting his PhD candidate. There it is. And we met him, first of all, when he was with Hilda Bay, though. So this is a good story, and take it away, Ryan.
Thanks, Greg, and thanks to Nick and Anna and everybody at the State Board for having me. I was really excited when I saw this year's program and sort of the themes that revolve around it. And I hope everybody here enjoys my talk. I see a lot of familiar names in the audience. And, this talk today is all about access and agency as it regards to beach water quality data. And I also want to really quickly thank my advisor, Allie Boehm, who was a collaborator with me on this project, as well as the USC Sea Grant program for funding this program, or for the project. So as Greg said, my name is Ryan Searcy. I'm a PhD candidate at Stanford University, and the name of this talk is A Day at the Beach, Enabling Coastal Water Quality Prediction with High Frequency Sampling and Data-Driven Models. So this talk is going to follow the environmental science and technology paper that was published at the beginning of the year. I'll provide a link to that and provide it for those who want it at the end of the talk. But instead of going into the weeds with the modeling today, I want to talk a little bit more at a higher level. So I'll first introduce beach water quality and discuss some of the access issues as it regards to beach water quality data. Talk about how predictive modeling can alleviate these issues, and then introduce a new technique that we've tested that enables increased access and agency to communities who want to know what water quality is at their beach. And then just for fun, in case you're zoning out while I'm talking, points for those who can guess where the pictures in the slides were taken. And a hint for this one, this was last year's #1 beach bummer on Hilda Bay's beach report card list. Okay, we'll get into it. It looks like the font's a little different in this, so I apologize if the animations and things aren't lining up perfectly. But first, I want to talk about why we monitor beach water quality. And the short answer is health and money. 90 million illnesses and costs of up to $3.5 billion annually are estimated as a result of poor water quality in the United States. So we monitor to give an indication of risk so we don't get sick when we recreate in the beach. And most water quality programs monitor fecal indicator bacteria, or FIB. These are proxies for pathogens like norovirus and salmonella, things that are correlated with acute illness like stomach flu, skin rash, ear, eye infections, etc. And FIB also indicate the presence of fecal pollution and sewage in the water. So in California, county agencies and city agencies are responsible for monitoring and public notification. And beach management decisions are made based on FIB measurements in water samples. So if FIB are measured in high concentrations, then beaches are posted as unfit for swimming. So that's all good and well, and people can access this information on county sites, and this is or community science group sites. But there's one big overarching problem to these programs in that it has a relation to do with access of water quality data. And I'll delve into that a little bit here. So studies have shown that fecal indicator bacteria can change in the environment at really high frequencies. There's lots of things in the environment that modulate their concentrations. They can move around and they can degrade over time. But our capacity to monitor them is much lower. In California, where some of the most robust monitoring programs exist, most of the 500 or so odd beaches that are monitored in the state are only tested once weekly. In addition, the lab methods that enumerate FIB take 1 to 2 days, so it could be quite a bit of time before a sample result is ready for the public to use to weigh or make health-based decisions on. And this is sort of highlighted in this figure here. This is typical FIB data. This is daily data. And the dots represents the FIB concentrations. Dots above the red line indicate water quality that would be out of compliance with the state's health standards. And the background of this plot shows the posting status of the beach at the time at which the sample was collected. And you can see the 1-day delay leads to sometimes a beach being posted when water quality is clean, and worse, unposted when water quality is actually measured to be dirty. So beachgoers never really have an up-to-date information about water quality is from single samples alone. Fortunately, predictive models are sort of are used to alleviate this low frequency information issue. So data-driven models in particular have been successfully used to accurately predict FIB standard exceedances, and those predictions are typically accessed via websites or apps, just like water quality samples are. So in congruence with monitoring programs, predictive models can lead to many more days of water quality information for beachgoers, which is a huge upgrade. And we'll dive into under the hood a little bit of what models look like. So models are functions of environmental parameters, meteorologic and oceanographic conditions that act as surrogates for the processes that might affect FIB concentration. So rainfall, tide level, wave height, those sort of things are typically environmental variables in these models. And these can be as simple as regression models to more advanced machine learning models like random forests and neural networks. And this is an example, let me see here. Oh, here we go. This is an example of a typical data science workflow for model development. You start with historical data, split the data into training and test sets, fit a model, test it, and then you can start using that model by applying new data to it. So models developed in this way, again, have been shown to provide more frequent and more accurate water quality information to beachgoers, quite a boon. And there have been dozens of studies in the literature verifying the uses of this, and they've also been endorsed by governmental agencies and bodies like the EU, the EPA, and the World Health Organization. And in practice now, we see modeling systems used at beaches around Ireland, Hong Kong, New Zealand, the US Great Lakes, and of course, I would be remiss without shouting out to my old stomping grounds, Heel the Bay, who runs the California Nowcast system. So in support with the State Water Board, you can find the predictive models on Heel the Bay's Beach Report Card website or Beach Report Card app, and I encourage you to check those out now if you're bored, or after the site if you're interested in what I'm saying still. This program in particular runs for dozens of sites around the state of California. Okay, so that's the state of beach water quality monitoring and modeling programs now, but there are still some key limitations that prevent people from accessing water quality information for their beaches. So one big knowledge gap was, what if there are no data for beaches? What if my beach isn't being monitored by a local agency, or we just don't have resources, or there are no resources for agency monitoring at these beaches? Under current methodology, as I mentioned, predictive modeling systems are only created for beaches that have these historical data sets that can be then plugged into this machine learning workflow. And when I say historical data sets, we're talking about 2 years of monitoring data at the minimum, but more likely 5 to 10 years given typical monitoring frequencies. So what we call data poor beaches, which have little or no past water quality data, are excluded from modeling systems. And this is a problem because many beaches, not only in California, but globally on the world's coastlines, can be considered data poor. So this is what motivated the project that I'll explain next. And what we wanted to learn was, are large historical data sets truly needed to say something about water quality at a beach, and thus develop models? So our research question was, can models for data poor beaches be developed using a new technique, and that technique is called high-frequency sampling efforts. So high-frequency sampling involves showing up to the beach, collecting abundance of water samples at one every half hour, one every 10 minutes for a discrete period of time, say 1 to 2 days, and then fitting models on that. And the thought was that if this technique, which is rather simple, albeit rather exhausting for those who have to implement it, if this technique is successful in yielding models that are valid and accurate, then this could be a way for a lot of data poor beaches to suddenly have a robust monitoring or modeling system for themselves. Okay, so I'll sort of just really briefly summarize that project here. So what we did was collect water samples during a number of these high frequency sampling events. We studied 3 California beaches shown here in this map. And we showed up to the beaches, sometimes only one day, sometimes up to 3 times. And We collected samples one every 10 minutes or one every half hour. We analyzed the samples for fecal indicator bacteria, as well as collecting associated environmental parameters. So we noted what wave heights, tides, the solar irradiance, rainfall, etc. And here's a raw time series of the FIB data from one of those events. This was an event conducted at one every 10 minutes. So let me orient your eyes here. These dark solid lines are the FIB concentrations of both Enterococcus and E. coli, which are two types of FIB. The dashed lines of the same color are the state's allowable thresholds above which beaches would have been posted if those samples were actually measured by a monitoring agency. And then the blue dotted line shows the tide at the time of the sample collection. And so you can see a lot of high frequency variability. There's often times where samples are measured at the detection limit, and then the next sample is above the state's allowable threshold. So again, highlighting the importance of not only using just single samples alone to sort of make a decision. The other benefit of conducting these events is that we saw some possible relationships with various environmental and time parameters. So what I'm showing here is, oh, and I see a little bit of a formatting thing. What I'm showing here is average FIB concentration collected at the events on the y-axis by the time of day. So we can see that as the sun starts to rise and solar inactivation is sort of kicking in, we see an overall average decrease of FIB concentration at these events, which is kind of neat. If you didn't know anything what was going on at your beach and you conducted an event like this, you could possibly find different environmental parameters that were important to FIB. And some of the more important parameters that we saw in addition to solar inactivation were tide level, water temperature, and offshore wind speed. Okay, so we took all of that data and then we applied that standard modeling methodology, really simple, basic. We fit regression models, random forest, neural networks, nothing too fancy as machine learning pipelines go. And we trained and tested nearly 126 different models. So this figure here shows the random forest model, which shows kind of a typical performance. The top plot shows the model in training, which, as we expect, models typically fit their training data rather well. And then we tested all of our models on future data, not only data collected at future events, but data collected by agency partners during their routine monitoring over the course of an entire season. And what we saw was that on average, models created using this high frequency sampling data could be used to accurately predict water quality for an entire beach season, which is a huge result. Okay, I'm getting a little warning. I need to wrap up here. So summary, what have we talked about here? So what are the take homes? Well, we know that recreating in poor water quality can get you sick, and knowing what water quality is can minimize or help you minimize that risk of getting sick. Predictive models can increase the frequency and quality of water quality data, which can be used to make health-based decisions. And our results of this high frequency sampling study is that they imply that with adequate support, agencies or groups like agencies, universities, tribes, community science groups could apply a high frequency sampling scheme and get models that predict water quality well for them. Okay, so what? Who can benefit from this? Well, community groups are sort of what we had in mind when we started dreaming up this project. So communities could create their own data and models and have agency over water quality at their local beaches, which is huge. They don't need to have governmental agency support to start giving themselves better information. But public health agencies could also benefit from this framework. It could be used to quick start a modeling system at a newly monitored beach or learn new environmental dynamics for water quality at beaches that are being monitored. And we envision that this could provide insight for other water data fields. So an easy one would be applying this for harmful algal blooms or applying this for river water quality, but possibly other water quality parameters could benefit from a high frequency sampling scheme. And of course, this would be something to investigate in further studies. Okay, so that's my talk. I can take questions now. I'm happy to talk about how I think communities could actually implement this. I can also talk about some limitations. Of course, that's always part of doing science, is things need to be sort of contextualized around that, and also future work if people are interested. So thank you so much.
Thank you so much, Ryan. That's great. Super awesome to hear your progress and to always hear that big picture view you have of looking at this. Do we have any questions for Ryan at this point?
Yes, we do. Kyle says, great presentation. What is the false positive / negative rate of the model predicting water quality above the threshold? How does this compare to the observed data rates?
So, so the false positive rate and false negative rate could also be sort of calculated around like sensitivity and specificity, which are typical model evaluation parameters. That is something that we looked at, that we did have on hand, but because we did this sort of as a bulk experiment, we had variation between the 126 different models. Some were poor and some actually did fairly well. What you'll find in the paper is that on the whole, model performance per predictive performance was higher than that of the current method, which is relying on just an old sample to say what water quality is today. So it's still an improvement upon that. I will point you to the paper to try to find actual metrics. It's been a while since I can point out what the metrics are.
Which brings the next question. Among the models you used, which kind of models worked best?
Like far and above every other was the random forest. That was just a super powerful model type for us. We had to do very little tinkering with it, unlike neural networks where your choice of hyperparameters could really just make a model terrible. The error rate, both in training and testing, was fantastic. That I just completely recommend for people trying to run modeling systems. They're just fantastic.
Great. Another question. Can you comment on the source identification based on these results, anthropogenic versus non-anthropogenic type analysis?
My answer is maybe. They're not process-based models, so they're meant to be applied at a point in space where water quality is being monitored. Though you could maybe parse out sources if you find it very important variables. So again, variables are sort of proxies for what's actually going on physically. Because a model might have a rainfall and a tide variable doesn't mean that the rain itself is contaminating, right? It means that rain is probably leading to runoff happening into the beach. So if you see rain as an important variable, then maybe stormwater runoff is what you need to look at. And if tide is a very important variable, then maybe groundwater discharge is an important source into your beach, or washing of rack into the water if high tide is an important variable. So it can kind of lead you into the right direction, but you would certainly need to dig into it a little further.
Got it. And did you try boosted regression trees?
We did regression forests. So they're very similar from my understanding. Again, we didn't go into like what I would call like some of the fancier model types that people are applying now. The point was like, could just something like out of the box work? Like, does this sort of thing work? And it was just sort of amazing that we could sample for a day or two, and that would be a sufficient amount of data to fit that. But I would assume, or I would venture to guess that more complex model types, tuning of hyperparameters would subsequently lead to even more accurate predictions at those beaches.
Got it. That's all the questions we have. Thanks, Ryan.
Excellent. Thank you so much, everybody.
Thanks, Peter. Thanks, Ryan. I look forward to the next conversation. As you know, there's a lot of work to be done and legislation being proposed on inland waters. And you and I have talked about the role that this could play in terms of make it equitable risk communication because of the putting sensors in place at the same time as high frequency and all sorts of cool ideas. So I'm really excited to keep in touch, and thank you for your time today.
Awesome. Thanks for having me.
All right. Take care. Next, we are honored to have Dr. Scott Coffin, for a second presentation with some other team members. We are sort of moving a little bit into, well, eventually we're going to get to a computer vision version of this machine learning topic. But right now we're going to hear from Scott and his team. And if you're ready, Scott, go ahead.
Thank you, Greg. Just requested remote control, so I should have access. There we go. All righty. Thank you very much. And really interesting project, Ryan. Really cool to see the how far this has come just since last year. So we're going to shift to thinking back about the topic I'm quite interested in, microplastics, which is an emerging water quality threat, and using machine learning to predict toxicity to understand how much is too much for humans and aquatic ecosystems. So first, I'd like to acknowledge my co-authors, Dr. Leah Thornton Hampton from the Southern California Coastal Water Research Project, or SQUIRP, Cowger from UC Riverside, and Drs. Merel, Kooi, and Professor Bart Koelmans from Wageningen University Research in the Netherlands. So the impetus for this work came from two pivotal legislation, both passed in 2018. The first is California Senate Bill 1263, which requires the State Water Board to work with the Ocean Protection Council to develop a risk assessment framework for microplastics by 2026. And also included in this is to recommend back to the legislature source reduction strategies based on particle characteristics that may make plastic more or less toxic to the environment. The other notable legislation for this that was the impetus for this work is Senate Bill 1422. This requires the State Water Board to, among many things, develop a health-based guidance level for microplastics in drinking water, so that when we monitor for microplastics in drinking water starting the end of this year, we'll have the best answer that science can provide to consumers about what does this actually mean for your health. So in order to answer these questions, we have been working with experts from around the world in what we're calling a health effects expert panel. It started in October and ending this year, actually this month. And the panel is focused not only on drinking water thresholds, but again, ecosystem thresholds. And we have lots of collaborators from around the world being organized by SQUIRP and working with local partners such as San Francisco Estuary Institute and some academic partners such as the University of Toronto. So what we've found is that in order to predict toxicity for aquatic ecosystems, risk assessors typically use what's called a species sensitivity distribution. And what this is every species has different sensitivities to a particular stressor. And if you line those sensitivities up into a histogram or a distribution, then you can have an idea of what concentration causes harm in what percentage of the ecosystem. And this approach has been around since the 1970s and is widely used by regulatory agencies around the world. The US EPA, Europeans, Japanese governments typically use this for setting water quality objectives. And what's notable about this approach is compared to any other approach that uses just a single species, an SSD is highly effective at predicting actual impacts when you compare it to field data. So the issue with microplastics is that you cannot just build an SSD with raw data. The size really matters when it comes to toxicity. And in the past, researchers have tried splitting up size bins by different arbitrary categories, convenient ones like looking here, 0.1 to 1 micron, 1 to 100 microns. And what you end up with is a lot of overlapping species sensitivity distributions that are different from one another. And what's notable is that each of these you're really cutting up the data in order to make them, and so you're dramatically reducing the availability of data in order to build these species sensitivity distributions, and it decreases your overall confidence in the numbers that you derive. So in order to understand the toxicity of microplastics, it's first critical to understand the diversity of these particles. Thousands of different polymers, continuum of shapes and sizes, colors, and adsorbed contaminants. Luckily for scientists, microplastics, like all particles in the universe, have predictable behaviors. Recent findings using high information and high throughput screening techniques have been able to build probability distribution functions so that we can predict the behaviors of these particles in different compartments, looking at the distributions of size, shape, and density. We can build a model particle distribution in whatever matrix we desire. Using these probability distribution functions, we can align data from effect studies that are typically done in what we call monodisperse particle characteristics, something like a single size of a sphere with a single polymer. Usually it's like a polystyrene sphere of like 5 microns or so. And in this case, I'm considering that an orange. In the environment, you never just find oranges. You always find a polydisperse mixture of fruit, like a fruit basket. And so how do you compare the apples and the oranges to a diverse interspersed mixture of fruit out in the environment? Luckily, we can use these probability distribution functions and a basic understanding of how the particles actually cause toxicity to compare these two in a reliable way. One of the principal things that you have to understand in order to make this alignment, or at least hypothesize on, is what is the particle metric that we actually care about? Is it the mass? Is it the volume, the surface area, or just the particle count? One could think that volume may be the predictor for toxicity if it's just the amount in the gut that matters. Or maybe the surface area is the predictor, as that correlates to oxidative stress. And so now that we have these alignments, we can now build aligned species sensitivity distributions as shown here. And what you see is that they're much closer together than just trying to split the data up by size. So another thing to consider when doing these alignments is that the sizes that we typically measure in the environment are quite different than the sizes that we can do experiments on. Most of their monitoring data in the ocean uses a manta trawl, which gets you down to about 333 microns, quite large particles that you can typically see with the naked eye. Toxicity assays go all the way down to 1 nanometer, and a lot of these studies are actually much smaller than the particles that we're monitoring out in the environment. So what happens when you align these data? Here we see the unaligned environmental occurrence data in yellow versus the toxicity study concentrations in pink. And you can see that the majority of these studies are testing at concentrations much higher than what you would find in the environment. If you align the data, all of a sudden we see that a lot of these toxicity experiments are actually using environmentally relevant concentrations. It's just that they were using measuring by particle count for many smaller particles than what we've actually been monitoring in the environment. And when you do these alignments and you extrapolate to the amount that you would find in the environment if you had used a smaller detection limit, you can see this overlap. So now that we've done these alignments and we know a lot about the particle characteristics, and we can we think that the actual shape or the size matters, I ask the question, does a microplastic's shape or polymer affect its toxicity in more of a qualitative way than just the volume or the surface area metric? So in order to tackle this question, first I looked at the distribution of polymers in the environment versus what we have in our toxicity database. And as you can see here, these orange and blue bars, they're not the same. And there's quite a mismatch going on here. sort of an artifact of the available polymers for toxicity experiments. The same goes for shapes. We see a lot of studies done with spheres in labs and almost no spheres in the environment. Fragments, we do have a lot of fragment data, and there's mostly fragments in the environment. But when it comes to fibers, we have almost no data. And fibers make up almost half of all microplastics in the environment. So in a way, we could be misrepresenting the actual toxicity if we're just depending on the current alignments, not taking into account these differences with shapes and polymers. What we know from lab experiments is that fibers are more toxic than spheres. In a controlled study looking at fibers, spheres, and then the mixture of the two, they found that fibers were more toxic than spheres, and even more toxic than the mixture of the two together. So in order to understand the relevance of shape and polymer in the toxicity of microplastics, I took the existing data set, which is made up of particle characteristics, test parameters, organismal characteristics, as well as effect endpoint data, and built different machine learning models to predict the toxicity, and then build species sensitivity distributions using environmentally realistic distributions. So the modeling objectives were threefold. First is, what parameters determine toxicity? Can we rely on surface area or volume? How reliable are these alignments, better than just using a particle count or something? Also, which exposure metric best predicts effects? The parameters to determine toxicity. If fibers are indeed more toxic than fragments, that's a significant finding that we should be reporting back to the legislature, as controlling the sources of fibers might become a higher priority for them than looking just at the fragments. And finally, can a model improve our toxicity predictions and make us feel more confident in the assessment of risks? So looking at the database, I mentioned this in my lightning talk this morning. We have a really rich but extremely diverse database. 167 manuscripts made of 6,000 measurements. We have 3 shapes and 14 polymers, so a lot of diversity, and then a huge range of particle sizes. And the real kicker here is that we have 117 species. Each of these species are extremely different in sensitivity, which makes building a single model using all of the data quite challenging, which sort of forces us to use more sophisticated modeling techniques. Looking at the relative feature importance, this is an output from Dalek's package, looking at the random forest prediction. We see that the organism characteristics and endpoints are by far the most important characteristic for predicting toxicity, whereas the actual particle characteristics didn't seem to matter as much. Looking at the toxicity by level of biological organization, we see almost no difference. This is quite interesting, as a typical theory in toxicology goes that you see more sensitive impacts at lower levels of biological organization, such as subcellular impacts being a predictor of what you would find in the population or organism level, but happening at lower concentrations. And what we're finding here is it almost doesn't matter when you compare it to other factors. The model predicts that fibers are indeed more toxic than fragments and spheres, which again is a significant finding for source control. And looking at which exposure metric best predicts effects, we find that we built a multiple linear regression models here and just swapped out the exposure metric. You can see here, going from left to right, we have decreasing model accuracy. So actually surface area was the most accurate model overall, but it had an R squared of 0.16 compared to the worst model of 0.15 of mass. So it doesn't seem like there's a smoking gun here about which exposure concentration we should actually be aligning for. So finally, can a model improve toxicity predictions? We tested a multitude of models. General linear model is easy to interpret, but gave the least predictive or least accurate predictions, whereas an extreme gradient boosted trees and random forest model provided more accurate predictions with R-squared values of 0.82 and 0.84. So in the end, we went with a random forest model for using our predictions. And finally, what we did was build a species sensitivity distribution by predicting the toxicity using different, by modulating the polymer and the shape types to what we'd actually find in the environment. So in a way, we are taking our alignments for the toxicity and then correcting for the bias in the database so that it's more representative of what we'd actually find in the environment. When you superimpose these distributions on top of each other, you can see the biggest difference is that the error bars actually shrink down when you use a model and actually use environmentally realistic shapes and polymers. Typically, the EPA and other risk assessors extract a single value for this for water quality objectives, and they report the standard error. And again, you can see here the environmentally realistic prediction. We see actually a lower HC5 or metric for that the EPA might use for water quality objectives. And in particular, we see a much lower standard error than what we'd find with just using the raw data and not doing any sort of predictions or corrections for environmentally realistic conditions. So in conclusion, this is really built on the data that we currently have, and we're seeing a dramatic increase in the number of toxicity studies that are published for microplastics every year. It seems like we're on an exponential increase, and as you all know, the more data and the higher quality data you have, the better models you can predict. And so we're really hoping that this is just the beginning of this. And as we get more data, we'll be able to improve our predictions over time. So in conclusion, the relative importance of microplastics toxicity as predicted by our random forest model is that the particle size is much more important than the polymer and shape. However, polymer and shape do seem to matter. The predictive power of exposure metrics, there's no smoking gun, but it does seem that surface area is better than particle count, which is better than volume and much better than mass. And we can use modeling techniques like this to increase the certainty of our risk assessments for predicting toxicity, not only to aquatic ecosystems, but perhaps one day we can apply this to human health as well. And with that, I'd like to thank you all. And I think we might have some time for questions.
We do. Thank you, Scott. That was fantastic. Mr. Haupt, do we have any questions?
It's not Mr. Haupt anymore. He is gone. So
Yes.
This is Bev. Hi, Scott. We do have one question. It says, great talk, Scott. How does the TOMEX model account for lack of sample representation prevalent in many microplastic studies due to low sample size or volume of the matrix?
So the question here has actually to do with the risk characterization. And it's a great question because the risk characterization is actually nested, it's actually embedded in our model because we have to rely on these probability distribution functions in order to actually even do these alignments. And so the model is able to account for the sampling bias to the extent that we have good data. And so we're really relying on a handful of very high resolution monitoring techniques that have actually used a representative or a good amount of sample volume to get a lower size limit of detection that's appropriate. However, those are for the water bodies that they monitored. So, they might be in the Netherlands or they might be wherever they source the data from. So ideally, you'd really want to get high quality monitoring data from the ecosystem of interest that you're deriving your water quality objective for to really feel comfortable about these assumptions that we're making.
Okay, thank you. We have one more question that came up. Is there any impact of color in the toxicity study? In fact, I'm wondering why color is important in the MP study where it has any impact.
We have not looked at color. I don't believe we captured that information. A lot of the particles that we do toxicity experiments on, they're so small that you can't really determine what the color is, other than perhaps through fluorescence or something, but optically, you can't really detect the color below about 1 micron or so, and a lot of our toxicity data is in the nano range. At this point, it doesn't seem like color is a great predictor, and just looking at the other particle characteristics, I would be really surprised if it was, considering we know that polymer is much less of a good predictor than size. And really, I would say it's the organism that is by far the most sensitive thing for toxicity.
Okay, we have another question that came up. Can you comment on the hydrophobic chemicals on toxicity studies? Will the conclusion change if HOC is taken into consideration?
So this current exercise was done without considering any adsorbed contaminants, basically only considering the particles themselves as they're used by the manufacturers before any additives or any hydrophobic organic contaminants have interacted with those particles. Looking at the actual chemical toxicity, the transfer of chemicals is a completely different modeling exercise, and it could be integrated into this. However, it seems at this point, based on the state of the science, that at least adsorbed contaminants from the environment do not seem to be relevant for microplastics toxicity. We have much greater exposure sources from other sources, and that goes both for humans and for aquatic ecosystems.
That's great.
Okay, thank you.
Thank you, Bev, for your help on that. And thank you, Scott, for your presentation and your work and your continued dedication to solving this problem. And I look forward to the next one. So thanks.
Thank you, Greg.
Next we have a great presentation about computer vision that I was really excited about, a little too early. But this is Lorenzo Flores. He's going to talk about how to make sense of detection and computer vision from the perspective of controlling trash, in particular cigarette butts. So Lorenzo, if you're ready, go ahead.
Yes, I'm requesting controls there. All right, am I able to advance? There we go. All right, my name is Lorenzo Flores, and I'm from, I represent the San Francisco Estuary Institute. My talk here is tobacco product waste monitoring methods, particularly cigarette butt detection using drone imagery and neural networks. This work has been funded by the California Department of Public Health. And I will call out some of the contributors at the end of this here presentation. So to start, let me just lay the groundwork here before I really launch into things, which is in order to go and assess cigarette butts or trash, which was some previous work that we've done within the field, there's a whole bunch of assessment methodologies that people employ, and it takes a lot of person power and time and effort to go out there and get a sense of how much of trash, or in this case, tobacco waste, is in our environment. So in this particular work, we're looking at tobacco waste products, which I will refer to as TPWs. And so what we want to do is we want to go from a conventional method where you send people into the field and figure out if there's a way to sort of do the same thing, but remotely. And so ideally, as you can see here, this is my coworker, Pete Kahanen, and he's our drone pilot at SFEI. And so the idea was, hey, what if we fly drones over an area and then use machine vision to identify whatever we're looking for? So in this case, cigarette butts, and hopefully one day, all sorts of tobacco waste. So the first point here is that the one of the benefits is that we want to expand the geospatial range, meaning that, if we're flying a drone, we can cover a lot more area than people out in the field looking for trash in our environment, or tobacco in our environment in this case. We can increase the temporal density. So that means we can go back consistently more often if it's just maybe one person or a team in a drone. That's very different from a handful of people to go out. So we can go out more frequently. it's a lot easier to collect this data than it is to go out and do counting. And we would like to automate said counting because, one step could be just taking drone imagery and then coming back to, to the office and then actually a human looking for cigarette butts. So, that's where the computer vision comes in. And we want to improve repeatability. So with this kind of approach, as I'll discuss in the next few slides, there's the opportunity to ensure that when we do go out, we're doing more or less the same methodology as we did before. It's a little harder to control for that when you have teams of people that you're sending out to the field. So as we see here, these unoccupied aerial systems, or drones as people like to call them, we fly above the ground, and the pilot can cover a lot more space than with an aerial vehicle than they can on foot. Apologies for that sound in the background there. And then on top of that, as you see here, so we use the software called SiteScan, which allows us to go ahead and draw a polygon over a space, and we can have the UAS or the UAV go out there, the drone, and go out there and essentially take images of that whole space, and then we can always come back with the exact same polygon coordinates, if you will, and take new data essentially. So you can go back right away or after a few years, and you can really monitor change over time for a given space. And so that's fantastic. So there's some constraints to bear in mind. You need to maintain a line of sight with the UAS, meaning that you have to see it at all times. So if you're on the ground and especially if you're in like a more heavily wooded area, that could pose an issue if you can't see your drone. You want to avoid obstacles. So this actually, this comes up in heavy environments, a lot of forests and whatnot, or trees, and then if in urban environments, you have telephone poles, and etc. You can't fly directly over people that are not part of your flight team. So this is yet another constraint to bear in mind. You can't fly near airports or other secure airspaces. There's exclusion zones. And here, heavily wooded areas. So on the opposite, if the drone is above you have line of sight issues, but B, they can't see under the canopy. So that can be an issue as far as data collection. And you can't fly in inclement conditions. So fog, rain, certain weather, you just can't go out there with the drone. And we do recommend an FAA licensed drone pilot for this work if you're going to go out there with the drone. So we have the imagery, and we want to do the machine learning component. So just very generally speaking, as I'm sure everybody here is now very much aware, machine learning, we're basically taking computers and we're using these machine learning algorithms to do something. So in this case, computer vision for identifying tobacco waste, cigarette butts in particular. So I mentioned here, so we wanted to adapt our general trash detection tool, but teach to detect cigarette butts. So we did some prior work where we essentially did the same methodology, took a drone, went out to wetland environments, and then flew said drone, collected a bunch of imagery, and then annotated the data for trash, and trained a neural network to identify trash. There was a lot of lessons learned. That was one of our first times doing this workflow. We learned a lot from that. So we decided, hey, what happens if we take that same methodology and apply it here? So let's go ahead and do this, but with very confined parameters. We wanted to really make sure that we could detect those cigarette butts really at different elevations, and another caveat being, hey, a lot of cigarette butts are probably going to be on blacktops, so let's go ahead and do this on blacktops. So as I called out before, yes, here machine learning can automate the counting of cigarette butts. So once again, this saves time of doing a visual survey. So on the ground, or even if I was back at the office looking at this imagery. So this is our method here. So we basically compared. So there's we used TensorFlow for this work, and in particular this faster RCNN neural network, and the way that using this object detection API. So essentially the metrics that are reported out during the training process have a lot of ways to sort of parse that out, and they're really meant for you to help to make the model more efficient. And so what we decided to do pretty early on was, for the sake of talking with people and really getting a sense of if this is doing what we wanted to do, let's go ahead and compare the detections we get in new data with human annotations. The idea being that sort of our gold standard, or the best we can theoretically do, is the same as a person that's going to sit there and look for these cigarette butts from the air. Theoretically, you could also compare with on the ground counts, but there's tends to be, especially if you have visual obstructions, that's a lot harder to match than a human that's looking at the same imagery. So in this particular case, the model we trained, we basically were able to identify 1,008 cigarette butts out of 1,021 human identified annotations. So there was a success rate of 98%. So it did pretty well detecting cigarette butts that humans had annotated in this test data set that we had set aside. And here's the caveats, which I've kind of alluded to, but essentially I did mention this one actually. We seeded the environment to aid in the verification of the accurate count. So essentially we went to black space, our blacktop, and put the cigarette butts out so that we could make sure that we had a nice, plentiful, data set essentially. It would be awful if there was this many out in the actual wild. We maximized the chances by, we limited to cigarette butts as opposed to other tobacco waste, tobacco product waste, because it can really run the gambit. As you've seen, there's Juuls, e-cigarettes. There's all sorts of different products out there now which look very different from cigarette butts. And we limited the background to asphalt. So essentially, we often refer to it as blacktop. And so the next step is we went ahead and did, train a model just on the blacktop, ran this experiment where we compared to human annotations just on blacktop. We said, hey, what happens if we go to grass or some other area with, actual other objects, something that's more indicative of actual environments where we would want to run this algorithm. This is a case where we just kind of went to an area on one of those drone images of some materials for the field work, and we were able to find, we're capturing part of the box and just random items within this image. And so essentially we get false positives the minutes we go to a more chaotic background, which means, hey, great, this works for blacktop, but how realistic is that? And if we want to take this to the next step, the next level, we really need to start integrating data that is that represents a broader environment. So one of the next steps, which we're so grateful to West Sacramento, is that they've provided some street sweeper imagery. What you're looking at here is a GoPro mounted on a street sweeper. And so actually right now, we're kind of towards the end of this, but we have a wonderful intern. His name is Rylan Hunt, who's taken on this work and essentially integrated the street sweeper imagery into our model training and has begun the process of evaluating performance and efficacy, et cetera. So, the idea here is that this is a lot more chaotic. Still, there's a heavy presence of blacktop, but it's certainly a good next step, and it's a wonderful data set we can use. So we can basically start getting into real world testing here for this methodology and the model, which we knew the original model wouldn't work very well. So essentially, right here's an example of blacktop detections. And then actually, I don't have too many images, so this is we'll still have to do, but on the lower right, you can see an example of detections over the street sweeper imagery where you've got cigarette butts with a little bit of stuff in the background. And the results are promising. We're getting, there's a lot of caveats and parameters to fine tune, but essentially we're getting pretty good results in that. We're getting anywhere between 80% to 90% of the annotated cigarette butts when we go over the test. Take a model, train a model over the street sweeper plus blacktop data, and go over some a test set that we've set aside. And the revised model. So essentially, this revised model is able to identify 184 cigarette butts out of original 1,021 in that blacktop test. So this is going back to what we used previously. It identified less cigarette butts, but that's because we've introduced all this extra data for the street sweeper imagery. So there's a lower success rate, but the model can now accommodate more chaotic backgrounds, which is very promising. And so essentially, our next steps are to one thing that we need to do is revise the street sweeper annotations. There's just a few instances where the annotations need to be a little tighter around cigarette butts, a few missed cigarette butts that we suspect are sort of seeping into this work. So we just want to go back through the annotations and just make sure that they're a little tighter for that street sweeper imagery. We want to continue evaluating this new model and tune parameters. Sort of the next step would be to go ahead and look at what parameters we can modify for the learning schedule. And in this particular faster RCN network that we're using, there's a lot of different layers that we can essentially try out different parameters to see if we get better results. And ideally, we can expand this detectability to other tobacco product waste. Like that would be amazing is to start looking for those joules, for those e-cigarettes, et cetera. And then operationalizing the model, which is essentially the process of taking a model that's trained, putting it on a server somewhere where people can then send images to get inferences from, and then we can tell them how many detections we found in a given image. Let's see. And then also testing out with mobile devices. Actually, we've done a little bit of testing with that as well, and it seems promising where, coworker goes out and takes some images where there's cigarette butts, and the success rate there is like 60%, but it's very promising still, because that would be a great use of an operationalized model where I could take a picture with a phone and then get a count. And so then on top of that, then this automation can complement these manual methodologies I was describing in the beginning. So essentially, I want to thank Tony Hale and Pete Kahanen and Rylan Hunt. And these three have been a big part of making this work happen with me. And questions, my email, etc.
Great, Lorenzo. Thank you so much. Really exciting to see the progress that's been made on this. And hopefully it looks like we have a couple of questions. Beth?
We do have a couple of questions. So Lorenzo, can this method be used to count natural features like nests or weeds?
I think that it's highly possible. The biggest thing is getting that data set. In the previous talk, there was that great slide that shows like the more data, the better efficacy you can have, and that's certainly our case as well. And I'd imagine that would be the case if you were going to go for nests and weeds. You just need to make sure you have that data set. There might be some out there, but once you have that, it's a matter of identifying an architecture that can work with the imagery you have. And then you kind of go through the paces of training and then testing. So they can. This model in particular probably wouldn't do a great job at that since it's trained just on those cigarette butts, but certainly the workflow would probably work.
Okay, thank you. And we have one more. What is the scope of picking tobacco product waste?
Yeah, I'm not quite sure I understand this one, the scope. I don't know if any of the other people present can have a sense of what.
One interpretation might be, Lorenzo, why was tobacco product waste chosen?
Yes. So tobacco, actually, it can. So it's actually a big contributor of microfibers and microplastics. Those filters they get into the waterways. There's a lot of waste generated from tobacco products, and including some of these like microplastics, et cetera. So that's one of the reasons why that is a big one that we really want to limit. On top of that, once you start talking about other tobacco products, like once again, e-cigarettes and joules, et cetera, they have a lot of plastic and a lot of materials that just aren't great, or batteries even. That's another big one. You get batteries, these lithium batteries that end up getting into the environment. And all of those can just really mess up our ecosystems.
So, and we have one more, and I guess this will be our last one. Can Waterboard use aerials to develop an impervious area footprint? I've heard of this being done from aerials.
Not sure what an impervious area footprint is. Out of my element on that one, I suppose.
There's I'll just say there's a Waterboard project that uses machine learning, computer vision to help inform the cannabis program, and they're using it. It's very similar to training the library for plastic or tobacco products, though. So you train it for what it looks for, but there are different ways to integrate different layers and data sets. And we're testing out how LiDAR and other kinds of data sets can be combined. You heard earlier today also, the audience did, that OpenET is able to do some estimation of natural settings. And so there is progress being made towards that, but I think the other thing to talk about, Lorenzo, is the exciting iteration of this project. And the tobacco sort of came along because at one point we had strong partners with Department of Public Health in the trash datathon. And I think you guys even got us, that's partly why you did tobacco product waste, right? Was because of them providing some support for that research.
Very much so.
Yeah. So this is super exciting stuff. And I look forward to hearing more as we move along. There's a really strong equity overlap too. And so I know that the trash data question in general is one that interests me and everyone. So Lorenzo, thank you so much for your time and your talk today.
Thank you, everybody. Bye.
And thank you all for being here today. This concludes the end of day one.